Hello and welcome to part 4 of Dev Maths and Stats course lecture 2. In this short video we're going to look at how to find the derivatives of exponentials and logarithmic functions. So if we expand this, we'll find that the rules are extremely simple. So let me just give you some justification for these very simple rules before looking at some examples. So here I've given you a chart, and in this chart the function is actually y is equal to 2 to the power x. This is using one of the examples from the collection of online visualizations from the earlier part of this lecture. So here we have the function f of x is equal to 2 to the power x, which is what it's showing you here. Now remember that what this visualization does is it plots a graph, and it gives you two things. It gives you the height of the function, which is the blue line, so that's the line of the function showing the value of the function, and then for any points you pick it draws the tangent and shows you the slope of the tangent, which is the definition of the slope of that graph at that point. So here at the point chosen starting point here, we can see that the value of the function 2 to the power of, this is about 0.6, 2 to the power of 0.6 is about 1.5 approximately. But the slope, meaning if we increase x by another 1, how much more do we go up, is 1.06. And what this applet does is it plots that 1.6 as a height here. So this height is showing you the slope of the curve, and this is the actual value of the curve. So if we move this along, we can plot the gradient here. You can see that the gradient gets steeper. So the gradient's getting steeper at this point. If I add another 1, then I add another 1.77 to the value of the function. That's the 1.77 plotted there. So if I just move this up and down, you get the blue line, which is the actual value of the function. The black line is showing you how much the function will increase from this point if we add another 1 to the x value. So this is the derivative function. So we have the original function and the derivative function, which is showing you the slope of this original function. And you should notice that the shape is really very similar. So the shape is similar, but it's not quite exactly the same. But why is the shape similar? It's because as you move along here, the slope is always positive and it's always getting bigger and bigger. So that's why these points are always positive above the 0. They're always positive and they're always getting bigger and bigger, just as the value of the function itself is. If we slide right the way down here, go to the left, the function, the blue line, is always getting lower and lower, and the slope is also getting lower and lower and lower, so which is why the black line is going down. So both are going down to 0. So the shape is very similar, except what we notice is if we compare the value of the function, I need to set to the drawing tool. If I compare the value of the function, it's always bigger than the derivative. So that's the blue line, it's bigger than the derivative. Okay. Because I moved it, it erased the drawing, so let me just repeat that. Okay. Now I think we can get rid of that. And now I'm going to go on to a slightly different graph by changing the value of k to 3. Unfortunately, you have to ignore these dots. I can't figure out how to get rid of those dots. So here we've got the function f of x is equal to 3 to the power x. So the next exponential function, this one 2 to the power x, this is 3 to the power x. So everywhere, if you drew both the blue lines, you'd find this blue line is higher because it's a bigger number. But what's interesting is looking at the gradient of this everywhere. Now, I'll just move this up and down and we'll get the gradient a few times. And here you can see again that the gradient is the same shape as the original blue line, because as the blue line gets bigger, the slope gets steeper as well. But this time the difference we notice is that the value of the actual function, which I forgot again to change to the pen, value of the actual function is everywhere it's less than the value of the derivative. It's closer, but it's always less than. So for example, if you come to here, where the value of the function is 2, the slope, if I increase by 1, the slope is 2.22, which is slightly higher. So we've got these two different functions. F of x is equal to 2 to the power x, f of x is equal to 3 to the power x. In both cases, the derivative has a very similar shape to the original function. In one case, the function is slightly bigger than the derivative. In the other case, it's slightly less. Now, what this means is that somewhere in between 2 and 3, there must be a number where you get this happening. How can I forget 3 times to select the pen? There must be some number here where the function is exactly the same as the derivative. There must be some point where that works. So let's just see if we can find that. So 3 is this one, 2 is this one. So somewhere in between these two, I think that's about as close as I'm going to get. If I take 2.7, so I'm doing 2.7 to the power x, and then look at the value of the derivative here. You find here it's actually exactly the same. Now the correct value is not actually 2.7, it's actually f of 2.71828, I think, and then it goes on. And this number 2.71828 between 2 and 3, that's a very special number because it has this amazing property and other properties, and that's actually known as just E, the constant E. I'm sure you're familiar with the constant pi, 3.14. E is another constant that's very handy in mathematics. And E is the number where, between 2 and 3, where the slope of the graph is exactly the same as the height of the graph. So f is exactly equal to f dashed. Okay, let's go back to Maple. And now we can see that this is indeed the rule that if you have a function where the function of x is equal to e to the power x, then this gives you the lovely rule that when you differentiate that, the derivative of the graph is exactly the same as the original graph, so nothing changes. And this is the single easiest thing you have to know on this course, is to differentiate e to the power x, nothing happens. It's e to the power x is the answer. So the gradient of this graph is equal to the value of the function itself. Fine. Okay, now with that you get sort of a free gift, which is how to differentiate log x, a logarithmic function. And let's just give you an explanation of that. So this time, no fancy graphics, unfortunately, it's my handwriting again. So what we want to do is we have y is equal to log of x, and you want to differentiate that. So you've got some graph like this, and you want to find the gradients of log x. So at the moment we don't have a rule for this, but hopefully you know that by definition this means that if we take the exponent of both sides, e to the power y is equal to x. And that's because the meaning of ln x is actually log base e, with that special number x. So this log base e of x is the same as log, the natural log of x. That's what it means. Remember that this means what power of e do I need to get x? And the answer is y. So e to the power, this by definition, this means that e to the power y gives me x. So that gives you this. So this we can now differentiate, because if we differentiate this, easier to write it this way around, x is equal to, I didn't mean to do this, sorry, is equal to e to the power y. So we can differentiate this, but this is good practice for notation, because now it's dx by dy. Usually it's dy by dx, but because we have x as a function of y, it's dx by dy. Now we can apply this dead simple rule. So let's work it out carefully. Differentiate this. It's just e to the power y. That does not change when you differentiate. So the problem is we don't want dx by dy. We want to get from here dy by dx. That's what you want. From y equals log x, we want dy by dx. But of course, if you have some graph like this, it's going on like this, and you're looking at the gradients, and this is a change in x, and this is a change in y, then dx by dy is estimated by this one divided by this one, so this divided by this. So if you turn this upside down, delta y divided by x, that means that's an estimate of dy by dx. So this is the inverse of this. If you flip this upside down, you'll get this one. So it's 1 over ey. Okay, so it's just the reciprocal of this. Dy by dx is 1 over dx by dy. And now we can have this because e to the power y is actually just x. So you have this rather weird rule that when you take log x and differentiate that, you get 1 over x. Just not slightly counterintuitive. You should be able to draw yourself a picture from the previous notes, if you like, of what does the graph of log x look like, and what does the graph of 1 over x look like, and you should see why it makes sense that the gradient of 1 over x, that the gradient of log x is given by the values of this graph. Okay, back to Maple. So as before, that's all the behind the scenes working. What you need to remember is these two rules, this dead simple rule and this rule that if f of x is log x, f dash of x is 1 over x. Then to apply it, dead simple, so here's 1. So you have a function that's e to the x minus 8x squared. Differentiate this, well, differentiate e to the x is just e to the x. Apply the same rules as before here, so 16x. That's that one finished. So it's combining with the polynomial ones. And here we have 4 over x to the power 3 minus log x. Now remember to deal with this one. This you can see as 4x to the power negative 3. 4x to the power negative 3. So 4 times negative 3 is negative 12. Negative 3 subtract 1 is negative 4. Becomes y over x to the power 4. That's the first part. And then log x, using this rule here, log x just becomes 1x. Okay, so again, a long time explaining the concept and the derivation of this, but how to apply it, which is what you have to do during the course, is this part is simple, I hope. So, as always, any questions, please ask me in the live sessions, but for now, thanks for watching.